Hi, welcome to Blackboard Sessions number 6. My name is Al Clark. Today we're going to be talking about amplifiers, and specifically we'll talk about how to right size an amplifier for your application. So what we're not going to be talking about today is, Class A, Class AB, Class D, vacuum tubes versus solid state, any of those kind of things, because those aren't really the relevant issues we want to talk about today. We're going to talk about amplifiers as a more generic item, and specifically power amplifiers. So one way we can think of an amplifier is a conceptual idea, which we're going to represent as a triangle. We have some input called X, that's our signal input, and we're going to have some output Y. And an amplifier typically has a gain, we'll call that K. So that gain might be, there's no real standards, it might be 20 dB, which is factor of 10, 26 dB, factor of 20, 30 dB, which is about a factor of 30. There's not necessarily an industry standard for that, but fundamentally it's K. And as an ideal amplifier, we have a relationship that Y is equal to K times X, which just basically means that if my gain is 20, my amplifier, if I put 1 volt in here, I get 20 volts out. And the idea of our ideal amplifier is that the input impedance is infinite, meaning that nothing gets lost, and nothing's loaded down in the input, and the output impedance is 0 ohms. And so what does that really mean? Well, first thing it means is that we have a relationship in a power amplifier that P, if we assume that we have a load here, we'll call that a resistor for the moment, R, that P is going to equal the voltage swing squared divided by R, where V is the RMS voltage. And what you can take from that in this ideal amplifier is that, because it's an ideal amplifier and has a 0 output impedance, that as R gets small, in essence if R became a dead short, 0 ohms, this amplifier would have to source an infinite amount of power, which is something that's not too likely to happen in anything you buy commercially. Nevertheless, it's a useful thing for us to talk about. If we're talking about most amplifiers, we have a power supply. I'm going to represent this as power supply of V. These are my supply rails. The amplifier will swing somewhat, just a little bit less typically than that rail and that rail, somewhere in between. But for our ideal amplifier, we'll assume it goes to those extremes. In a vacuum tube amplifier, you might have a little different relationship because you probably have a step-down transformer. And you could also have situations where these are not equal, but we'll just assume they're equal for our discussion. This would be still true of virtually all solid-state amplifiers. So when we think about this for audio purposes, this resistor is replaced by a loudspeaker. If it's a passive loudspeaker, there'll be a crossover in front of it, and it'll be doing the full range. And if it's an active crossover, there'll be the crossover will be in front over here, and this will connect directly to the speaker. But fundamentally, we can think of this loudspeaker as being connected to the amplifier. If our speaker cables have 0 ohms, because they're also ideal, then we're going to put all of our power more or less into the loudspeaker when we can. Now, what does this mean? Well, the first thing you can take from this is that that we want to put as much voltage in this, because the more voltage we put in this, the more sound pressure level comes out. And this is the first take, because we talk about power amplifiers and power, but in fact we mostly care about voltage. How far will this amplifier swing? Because the sound pressure level of this loudspeaker is going to be a function of how many volts go into it. And if this is an ideal amplifier, it doesn't really matter what the impedance of the loudspeaker is at all, because we'll just keep supplying current until it's a dead short. So one of the things I don't like about the way we think about power amplifiers is that it's actually more useful most of the time to think about how many volts it swings. And you can calculate that pretty easily, because if you know the supply rails, or more importantly how far the amplifier can swing, that's the V peak, and you can and that's actually related like this, which is the art how to convert peak, assuming this went to the full rails, in this case V plus, or say, and we multiply it by this, and if you do the math here, this will be V peak squared divided by 2R. So why do I care about that? Well, the first thing I care about is that when I'm talking about right-sizing an amplifier, there's a very, very simple rule we want to apply. And this is a really important one. If we assume that our amplifier for reproduction needs to be linear, means that if I put a little signal in, I get Y equals X, this, and if I put a large signal in, I still get Y is K times bigger. That's what linear means in this context. So if we're doing linear systems, then the amplifier needs to be big enough to supply enough voltage for that transducer, whatever that means, to be as loud as we possibly want it, and after that it doesn't matter. So if we've decided this driver has to be 120 dB in loudness, and it takes some voltage to do that, more than that doesn't help us anymore, because we've hit our limits. At some point, the loudspeaker is also not linear because it hits excursion limits, other kinds of things. So we make some determination of how big the amplifier should be based on our sensitivity of our loudspeaker. If it's a passive loudspeaker, that amplifier in general would be bigger because it has to supply power to all the drivers, and it has to waste power in the crossover. If it's an active system, we're going to have multiple amplifiers, and we might have a big amplifier for the woofers and a much smaller one for the tweeters. And it's also a function of the sensitivity of the loudspeaker. Some loudspeakers take very, very little voltage to get very, very loud, and they're very efficient, and others are just the opposite. And so you might need a very large power amplifier in one case and a much smaller one in another. So why do we care about that? Well, the one thing that makes any amplifier a bad amplifier, no matter how you built it, is called clipping. And most of you know what clipping is, but I'm just going to explain what really happens. We've got some signal coming in, comes out here. If I put a sine wave in, I get a sine wave. It still looks more like a sine wave. That's good. But as we start running this at higher and higher levels, at some point, we run out of supply rail. Or if there's a transformer, we still run out of some kind of supply rail, and it starts clipping. So when you look at distortion of an amplifier, it's going to be probably pretty low, and then the distortion curve does like that, and that's the clipping points in here. And so we're not talking about subtle distortions of a little bit. We're talking about horrendous distortion at this point. When you have clipping, if it's symmetrical like this, it creates odd harmonics. If it's unsymmetrical, in other words, one side clipped, say, first, it creates even harmonics. Neither one are going to sound pleasant. I'm not talking about very subtle distortion now. We're talking about hard clipping. And so the first thing to take from this discussion is any amplifier, no matter how good you think it might be, is a bad amplifier when it's clipping. And in a practical sense, as amplifiers get close to their clipping point, they usually get a little bit nastier too. So we don't want to be right at clipping, but we'd like to be operating somewhere. If that amplifier clips, we'd be much happier if it was constrained to some region like this. So clipping is not a subtle distortion, it's horrendously bad distortion. All amplifiers that clip are bad in that context. So what does this kind of mean? Well, it means that when we're picking our amplifier, we want to make sure that we have enough headroom so it doesn't clip. But having more headroom than that doesn't really help us very much. So why is that? Well, maybe it weighs more, maybe it dissipates more heat, maybe it costs more, maybe it takes more space if it's a powered monitor, any number of things. So there's a point where having an amplifier just big for the sake of big isn't necessarily an advantage anymore. So, but we definitely want to err on too big versus too small. The second thing to consider is if you look back at my equation up here, or easier this one, is that if I have an amplifier that's rated at 500 watts, and we'll say it's an ideal amplifier, into some impedance, we'll say, it doesn't really matter, and at the same impedance that I can get an amplifier that's 250 watts, you say, oh, well, 500 is definitely a lot bigger than 250. From a sound pressure point of view, it increases your maximum sound pressure by 3 dB. That's it, 3 dB for twice the power. So if the loudest I wanted my speaker to be was 120 dB with 250 watts, well, 500 watts would, assuming it was linear, would be 123. So there's a diminishing returns here because as you start getting bigger and bigger amplifiers, at some point it costs a lot for each additional watt. So how many volts does my amplifier swing? Well, it may be in the data sheet, and I'd rather know that than the power. But you can calculate by just working this equation backwards. So if you've got an amplifier that swings 70 volts, actually 70 volts, which means the rails are probably like 75 perhaps on your amplifier, it'd be 70 volts squared. And let's say that was into 8 ohms for sake of discussion. That'd be divided by 16. That's 4,800 divided by 16, which in round numbers is a little more than 300 watts. If I want to know how much power was into 4 ohms, that number is half that. And so now I have, round number 600 watts. Now, that of course assumes that the amplifier can actually swing that kind of, deliver that much current. And in practical sense, a lot of amplifiers really can't supply, they're not ideal, and because they're not ideal, they don't really provide this kind of power because they have to dissipate heat inside the amplifier, and there's internal resistances and so forth. But it's a good way, and you can work backwards. If you don't know how far this thing is swinging, you can just work backwards by just saying, oh, well, what's its power rating, a couple of different ratings, 4 ohms or 8 ohms, and you can work and figure out the voltage. But, so when I'm right sizing, there's a second problem. This goes more to active loudspeakers. So you probably need a pretty good, well, let's back up for a second. So how do I figure out how much volts I need? Well, you can calculate all that and say, well, the sensitivity of this loudspeaker is this, and I have all these things going on. I've got crossover, it's boosting here, and I've got this box doing this. Or you can do the easier way, the poor man's way, if you will, or the simple way. And that is, I could simply measure, say with an oscilloscope, that's my oscilloscope, not a very good one, and I could just measure across the loudspeaker, and I could start playing it loud, and I could simply watch with, say, a music source or a sinusoidal source, but I could watch, and I could just watch for clipping, or measure how many volts it swings for a given sound pressure level, and I could then extrapolate up if I wanted to, so I don't have to go all the way to full scale. And that's a very, very easy way, because if you notice it gets really loud and it never swings more than 20 volts, well, there's half your answer. Because now you know roughly how big the amplifier has to be just from that. So, the second thing, how do you get more voltage? How do you get bigger amps? Well, one way it's common is through bridging. So in bridging, I have two usually identical amplifiers. And this first amplifier, when I have the load connected to ground, this is known as a half bridge. And it has this supply. But if I here's my V plus, V minus again. If I take a half bridge amplifier in general and I put an inverted signal into the input, and I connect the load now across the two, this is my speaker, let's say, then when this one swings kx, and that's inverted, this swings minus kx, effectively what I've just done is double the voltage swing. And what that's going to do is that's going to give me 6 dB more output, or 6 dB more signal to noise. It's going to total system-wise, it's going to quadruple the power because the voltage is squared, or in individual amplifiers, each one's double in its power requirement. But that's one way of getting twice the voltage swing. If the amplifier is already supplied as a full bridge, in other words, this and this is built internally, you can't do this. And some amplifiers are built this way intentionally, so you need to know that. Also, on the little oscilloscope myth that I told you about, how do I know If it's a bridge system, how do I measure it? Well, your oscilloscope might not really want you to go from here to here across the thing, because it may not be happy with both sides, with the ground side connected to a hot side. So what you could do there, if you have a full bridge configuration, is just put put some large resistors here, tie that to your scope return to channel 1 here and channel 2 here, and subtract the 2. And that's a trick that you could do for the oscilloscope measurement. So really what I think you're going to find in a typical active loudspeaker system is you're going to find that you're going to use a relatively large amp maybe for your woofers, and probably much smaller ones for your tweeters, and there's a very good chance you'll want to bridge your amplifiers. And that's really about the extent of what I wanted to talk about today. Thank you.